Hello, and welcome to my talk on methane odor abatement simulator with digital twins. My name is Derek Hollenbeck, and this is joint work with Dmitry Zolovek and Yangchuan Chen. In this work, we'll present the motivation and background, the digital twin framework, the MOABSDT case study, and then conclude with some final thoughts and future work. The importance of methane emissions from an environmental standpoint is primarily due to the fact that it's a powerful greenhouse gas. From the image on the top right, we can see that methane accounts for about 10% of the total greenhouse gases emitted, which is comprised of natural gas systems and landfills. But from the image on the bottom, we can see that in a 20-year time span, methane is about 84 times more potent than CO2. And mitigating methane emissions can help reduce global warming impact in the near term. Methane can also come from natural ecosystems such as the thawing permafrost, vernal pools, small lakes and ponds, as well as anthropogenic sources such as pipe fittings and valves, as shown as the image on the right from a FLIR thermal infrared camera. Extreme weather events are also of concern due to the changing amounts of greenhouse gases in the atmosphere. And when these gases go undetected, such as fugitive gas leaks, they can pose serious safety issues, such as explosions. Methane reduction and mitigation can be done through early detection and repair. Conventional methods typically use foot-based measurements with a flame ionization detector and use method 21, which limits some other technologies from being used. It also requires that all leaks be repaired, no matter the size. Advanced methods are being developed that use vehicles with cavity ring down spectrometer, or by plane with LiDAR, or by drone with lightweight spectrometers. A recent super emitter program by Picard and PG&E showed that leaks emitting greater than 10 standard cubic feet per hour contributed to 37% of their total emissions. So by focusing on the largest leaks first, they can mitigate the most amount of methane. In the image in the bottom right also shows there's discrepancies between conventional inventory-based measurements, bottom up, which is in green, and top-down approaches, which in this case by Johnson and others, is airborne-based measurements that still need to be resolved. So first, what is a digital twin? As many probably are aware, from Michael Greaves in 2007, a digital twin is a virtual digital equivalent to a physical product. It can be seen in early work such as the NASA Apollo missions, where you have a hardware twin, or flight simulations such as the Iron Bird, where you have a mixture of software and hardware twins, or today where you have manufacturing implementations, smart cities, or even cyber physical systems such as the robot Baxter by Werner and others. In this work, we want to focus on a definition such as the one proposed by our lab, where a digital twin is a combination of multiple individual and detailed simulation models, continuous, discrete, or hybrid, where it's an interconnection represents the dynamics of the complex system, which is updated periodically, windowed or real time, with the system information in order to reflect the system's current status as well as predict its future behavior and possible faults. There are many levels of digital twins. In the early development, we start with the level 1, where we have a digital twin environment. The physical system isn't built. There is no system interaction. There is no smart capabilities. And it's used typically for some preliminary design aspect. The level 2 digital twin is based on the real system. It operates standalone. There is no interaction between the two systems. It's not quite smart, and it can be used for performance analysis and system status. And as we progress through levels 3 and 4, we see that the physical system and the digital twin start to have real-time data acquisition, and there is increasing and smarter control, as well as more features such as fault diagnosis, prognosis, making recommendations, as well as automating actions over the physical system. There are three basic challenges in developing digital twins. The first is subsystem modeling. So what level of detail we want to implement, whether we use finite elements or discrete systems, whether we include multiple physics, multiple components, is there degradation? The second is the sensor integration and data fusion. So how are we getting the data for the modeling? What kind of computational requirements are there? Is there any protocols for gathering the data? And the last is behavioral matching, which makes the system, the digital twin, behave as the real system. And this typically comes in the form of our system knowledge, as well as what equations we can use to actually behavior match the systems together. The digital twin can be constructed in 5 steps roughly. The first step being the target system definition. This is all of the desired requirements, such as the simulation controller, the digital twin level, the purpose of the system. The next step is the system documentation. So what types of control algorithms we want to use, what are the specifications of the actuators and sensors, what are the troubleshooting and common problems we might find, what types of signals and processing we will be doing. The next step is multi-domain simulation, which could include a combination of data-driven models, stochastic and probabilistic models, deterministic models. The next step is the digital twin assembly and behavior matching. So this is connecting the input and output between the digital twin and the physical system, closing the loop in a way that we can do the behavior matching, and choosing a suitable optimization or strategy, such as a genetic algorithm or stochastic gradient descent. The last step is the digital twin validation and deployment. So this is validating the digital twin's behavior, typically in an offline sense, from data that the digital twin hasn't seen. This can include the developing the supervisory system that allow for real-time data management between the digital twin and physical system, or visualization, as well as allow the digital twin to operate in parallel. And upon doing that, it opens up a lot of opportunities to have smart digital twin capabilities for doing prognosis and autonomous capabilities. The MOABSDT case study is built around the Methane Emission Technology Evaluation Center, or METEC, shown in the bottom right. This is based out of the Colorado State University and is designed to emulate oil and gas industry-based equipment and offers a variety of controlled release points above and below ground, which are spread throughout the site. And for scale, there's a shot from a survey by Aerometrics in the top right. In a single blind intercomparison by Rav Kumar and others in 2019, part of the Stanford EDF Mobile Monitoring Challenge, has shown that drone technology can perform quite well, where they had a lot of true positives and true negatives, and they are able to quantify leak rates relatively accurately. The first step in our digital twin case study is our target definition. So we want to create a digital representation of METEC that can simulate short timescale behavior of the emission dynamics. And it provides us with some real-time or near real-time operation. We want to create a level 2 digital twin so that we can analyze detection and quantification strategies. And we want to conduct some offline control to study how environmental variables impact the digital twin in finding the source location, atmospheric stability, topology. And we want the overall purpose to connect these two together so we can run virtual controlled release experiments. The next step in the digital twin is the system documentation and known problems. So if we start that we don't have direct feedback from the level 2 digital twin. The control algorithms seek to perform analysis in the offline sense, such as behavior matching using synthetic and real-time series data, such as the paper in 2020 that we put out, as well as estimating source location from sparse sensors, which is a recent paper we did in the IDETC. The vehicle dynamics and motor inputs can be treated as a subsystem in a guided control mode, such as single or double integrator dynamics. We measure wind as well in a static or in situ way. We have to do upwind and downwind measurements to identify the leaks on the site. And we know that multi-emissions are difficult to distinguish. So if you have multiple emissions, it could affect your overall emission measurement, as well as onboard computers can store and relay information to the ground station. The multi-domain simulation we chose to focus on is POSIM, which in general aims to solve two PDEs, the first being the advection diffusion equation, and the second being the viscous-Burgers equation. This is based on the work from Farrell and others in 2002, which is based on a 2D model. And this 2D model can be power loss scaled depending on atmospheric stability. For instance, in a neutral condition, alpha here equal to 0.7, and z is the altitude of the measurements. The digital twin is assembled and behavior matched by connecting first the wind field model with the chemical filament dynamics and the collision model, which is shown on the far right, where we take METEC and create a virtual representation of METEC. The interaction between the sensor and the actuator models in space and time can give us measurement data, which is then used to provide for the behavior matching of the system. The digital twin can be validated by comparing the measurement and quantification results, such as shown on the top right, where we first try to detect the source by surveying all of the equipment. And here we found a leak near these 3 tanks. And then through quantification, so by performing a mass flux balance, we can see that there are small pin-like measurements going through this plane, which are both on the low level as well as the top level, which indicate the plume moving through these 3 tanks as shown in the simulation. A well-defined digital twin that's trained will produce results that can be suitable for prediction. And this digital twin can then be deployed to run in parallel with the physical system, which this opens up possibilities for online behavior matching, so learning key parameters such as source location, source strength, as well as provide for a smarter path planning. If we know where the plume is, we know roughly where we should start putting the sensors and actuators in space. So in this work, we introduce a MOABSDT. Just to recap, methane is an important greenhouse gas to reduce, and mitigation can be done through early detection and repair. POSIM and the collision model can be used to represent a level 2 digital twin. The digital twin of METEC can be used to study UAV-based emission quantification methods. In the future work, we'll look at conducting a series of these digital twin simulations to evaluate different UAV methodologies and techniques. We also want to understand how these meteorological conditions, such as wind speed or turbulence, might affect the performance, and it'll help us identify what the best practices are.